Hello, welcome to the lecture for this Friday. Today we're going to talk about 3.2, or at least start out with that, which is a better way to project. Before in class we derived a way to project onto a line of angle theta, and the formula worked and it was great, but it's not a great way. So for instance, what if we wanted to instead project onto a line defined by a vector instead of just onto a line of a particular angle? Also, what would we do if we were in higher dimensions and it wasn't quite so clear what we should do? So this way is going to be simpler. It's going to be better in general and more useful. So let's say we wanted to project B, a vector B, onto the line defined by a vector A. Well, how could we do that? Well, let's draw a picture. And it's going to be very similar to the one we had before. Let's say this is our line. Here's our vector A. It doesn't really matter where on this line it is, but let's say it's there. And let's say here's our vector B. If we want to project, remember, we want to find the closest point on here. Or another way to say that is we want to find the line between these two so that it gets 90 degrees. That will give us the closest point on this line. So, if we talk about this, so the projection should be some multiple of A, right? Because it's on the line defined by A, and so it's some multiple of A, positive or negative. So projection is going to equal, say, x hat A. So x hat is just some number. So in this picture, if we have P being the projection, right here, then, and this point is B, this line is A, this line right here is B minus P, right? Or P minus B, depending on which way we're going. What we want then is we want the line between them to be orthogonal to A. Remember, that's what we meant by the projection. That will give us the closest point. So if we use this formula, this says that we want A, B minus x hat A to equal 0. Well, this by definition is A transpose B minus x hat A. We can distribute the A transpose. We get A transpose B minus x hat A transpose A equals 0. The reason we can distribute the A transpose past the x is because x is just a constant. It's just a number, so it doesn't really matter. And then we can solve that. So we get x hat is equal to A transpose B over A transpose A. Remember, A transpose A is just the inner product. So we could rewrite this as inner product A with B over inner product of A with itself. But A with itself is the norm squared. So this is just AB divided by the norm of A squared. And that's exactly, so this is the formula for the length. And to just finish this up, right, this means that the projection is AB over norm of A squared times the vector A, right? Because a projection should be a vector, so this was a number, we need a vector. So there we go. This is the formula for a projection onto a line defined by a vector. So notice one important thing here is if the length of A is 1, if it's unit, then P is particularly simple, and we get this formula. The reason why we have this divided by A squared is because essentially the size of the projection shouldn't depend on what vector we choose on our line, right? All the vectors on the line should give the same projection because it's the same line. And so what this does is this normalizes it, if you will. So if we double the size of A, we double, that means we quadruple the top, but we also will quadruple the bottom, and so we'll get the same projection either way. It will give us the same vector, which is exactly what we want. So that's good. All right, so this is fine and all that, but it's not a matrix, and before we had a matrix, and so we still want a matrix. Projection is a linear map, so we should be able to construct a matrix from this information, and it's not too hard. So projection of a vector B, if you remember, just write it down again, was this. But this is just a number. So there's no reason why we couldn't just change the A to the other side. So it's A transpose B over A transpose A. But then now, this is just a number, so just ignore it for a second. We can multiply the top in whatever order we want. And so, I mean, we can just rewrite this as A transpose over A transpose A times B. So B is the thing that we were putting in, right? Is projection of B. And this, it turns out, is a matrix. And I mean, like we can just do a really easy example, right? If we had A is equal to 1, 2, 3, A transpose is equal to 1, 2, 3, 1, 2, 3, which is 1, 2, 3, 2, 4, 6, 3, 6, 9. Like that. Okay. So this is the projection matrix right here. And you can check if you really want to. You can check that the angle formula that we gave earlier actually is this. If you work through it, you'll find that they're the same thing. So one thing that we have here is, as before, the projection squared is itself. Now we know that because it's projection, it has to be. But it turns out that if you multiply this by itself, you can check that you in fact get the same thing again. It's not too hard of a calculation. So, one other thing to notice. This matrix has rank of 1. Remember, rank is the number of linearly independent columns. But if we look, our matrix, this bottom part is just scaling, so we can kind of ignore that. But when we multiply these two vectors, like this, we are taking 1 times this vector, 2 times this vector, and 3 times this vector to get our projection matrix. Which means that each of the columns is just a multiple of the first one. And because they're just a multiple, that means there's only one linearly independent column, which means that it's rank 1. So projection matrices onto a line are rank 1. In general, if it's projection onto like a 3-dimensional space, would be rank 3, but this is, we're only talking about dimension 1 right now. Alright, so this is the better way to project. If you may recall this formula from the extra proof that I gave, which is, when I write it like this, I had something like V1 x over norm of v1 squared v1, and I was subtracting this off of x. This was the projection. What I was doing is I was subtracting off the projection in order to make it orthogonal. We'll talk more about that later in a couple of sections, but it's because of this projection that we're doing here that we can do that so easily. All right, so next, we're now going to just say a few things about inner products that are interesting. So the first one is this, cosines. So we said that the inner product of A and B are 0, the inner product of two vectors is 0, if and only if A is orthogonal to B. In fact, this was our definition of orthogonal, and then we showed it worked in R2, and it works in NERN. It's harder, this doesn't really make sense if we're not talking about Rn to talk about angles, but we can define it this way, right? We can define that they're orthogonal. So, we proved this for R2 using the Pythagorean theorem. Essentially, this is a consequence of the Pythagorean theorem. For the Pythagorean theorem to hold, if the Pythagorean theorem holds, that means we can talk about the two sides being A and B. And then this is the condition given to make sure that, this is the condition given to make sure that the Pythagorean theorem holds. Well, we can do something similar but more complicated. From way back when, you may remember the law of cosine, which is very similar. It's essentially the upgraded version of the law of sines. Or sorry, of the Pythagorean theorem. So this says that if you have A and B with an angle theta between them, then, and this side is C, right? So now we have an arbitrary triangle rather than a 90-degree one. It's more complicated, but the formula that we get, the equation that we get is a squared plus b squared equals c squared plus 2ab cosine theta. You know, if cosine is positive, then, you know, c is a little smaller. If cosine is negative, then c is a little bigger, as we would expect from this picture. So, using this same picture, we can derive something, if we change A and B and C into vectors instead of lengths on a triangle, and we use the same thing, we use the norms just like we did with the Pythagorean theorem, and we reduce it a little, we find that the cosine of theta is equal to A transpose B over norm of A, norm of B. Or another way of saying this, just the more common way of writing it, is that the inner product divided by the norms gives you the angle. All right, so it gives you the cosine of the angle, of course. So this is an important rule, and really we're going to take this as a definition, but this is the proof that it works in R2. It works in R2 exactly because of the law of cosines. So this lines up with what we knew before. If they're orthogonal, if A and B vectors are orthogonal, then A comma B equals 0, so cosine of theta equals 0, and so theta has to be pi over 2 or 3 pi over 2 if you want to be, you know, if you want to say that one. But in any case, the point is that both of those angles represent when they're 90 degrees away from each other. Just one in one direction, one in the other direction. So, the inner inner product, what it really does, one way to think about the inner product, is that it tells you, it gives you lengths of the two vectors, because that makes sense. And you know, if we double the size of A, we want the inner product to double. It gives you the size of A and B and the angle. That's the information contained in the inner product. So we can define an angle to be this, or you can think of it as the inner product gives you this in Rn. So, okay. So this leads to an interesting conclusion. And the conclusion is one of the most important theorems in mathematics. It's used all over the place. And this is called Cauchy-Schwarz. I have no idea if Cauchy or Schwarz came up with this. There are a few theorems ascribed to people who never actually did the thing that the theorems say. But this is the Cauchy-Schwarz inequality. And this is the inequality. Well, cosine is between 1 and -1. And so we can use that over here, and we can say the absolute value of this inner product has to be less than or equal to the norm of A times the norm of B. The proof is that cosine of theta, the absolute value of the cosine of theta is less than or equal to 1. So that's a really easy proof, right? Of course, we had to prove this first, which took the law of cosines, which took a proof of the law of cosines. It's not completely trivial, don't get me wrong. But at the same time, it's, yeah. There are, I should mention, there are 2 or 3 or 4 or 5 other proofs of this. Just like there's 2 or 3 or 4, 100 proofs of the Pythagorean theorem. And, you know, for instance, in my 170A class last term, I used a completely different proof. We didn't talk about angles at all. And there's actually a whole other proof in the book, a second proof. But it gives you the same thing. Inner products, again, inner products give you lengths, and then they also give you an angle. And this is true, it turns out that this is true no matter what inner product you're talking about, as long as you use the norm that's defined using that inner product, right? As long as you're using the inner product given by, the norm given by the square root of the inner product of the vector with itself. As long as you're using this kind of norm, this is true for any inner product, which is pretty cool. The proof that we gave does not work for any inner product, but, you know, whatever. We didn't have time to talk about it, so whatever. All right. Well, so that's it for 3.2. The main part there was just, we need to do projections, we need a better way to do it, and so we did a better way. We came up with a better way. So the next topic is 3.3, which is about projections and least squares. So let's just give an introduction to the least squares problem. So say we want to solve something that doesn't have any solution. So let's say 2x equals 2, 3x equals 3, and 4x equals 5. Now, clearly this has no solution because, well, these two require x equals 1, this one requires x equals 1.25, so there is no solution. This is unfortunate because we might really want a solution. So for instance, this could happen if we did an experiment and we wanted to see what this x was. So for instance, this could, to come up with something random, if you pull a spring out 2 meters, or not 2 meters, say 2 centimeters, the spring might exert 2 newtons of force. If you pull it out 3, it might do 3. If you pull out 4, it might do 5 newtons of force. More likely, actually, it'd be like 3.5 or something, but whatever. Just as an example. The point is that your data, the amount of newtons that the force takes, the force is pulling on your spring, might not, is going to have errors. Your data is going to have errors. And in fact, this column over here could have errors too, its own errors. And so because of that, even if in the underlying reality, there should be a solution, a perfect solution, in general, you're not going to get one because you're going to have these errors that kind of make things random and not quite line up. So even if you're right, you might not get a solution. So what we do instead is we want the best solution. And of course, there's no solution, but we want to get as good as we possibly can. So what we say we want is we want the error to be small. And if we want the error to be small, that means we need to define what we mean by error and what we mean by small. But that's not too hard. So if we were to have an exact solution, we would know that AX equals B. To go away from this problem, to go to a general one. If we had an exact solution, we would have AX equals B. Or in other words, AX, which direction do you want to do this? B minus AX would equal 0, to move it to the other side. This is great, but it's not going to happen, right? Generally. So instead, what we say is we want the error B minus AX to be small. So E is our error, it's just B minus AX. And a lot of books will also call this the residual. I should probably write that down. Because it's the residue left over after you do this. You come up with your solution. So this is essentially, if we minimize E, if we make E as small as possible, E is a vector, so we have to talk about what we mean by making it small. But if we make this as small as possible, that means that our solution, it's going to be as close as possible. We came up with the X that's going to give us the closest thing over here after we multiply. So, what do I mean by small? Well, if we want it to be small, small means we have to choose some way of saying small. So let's say the norm squared, or equivalently the norm, is small. So, we want this error to be as small as possible. Now the question is, of course, how do we do that? The book gives an interesting derivation in terms of derivatives. It turns out that this is a quadratic in terms of x, multi-dimensional quadratic. So it's a bowl, and so if you take the derivative, you can find where the derivative is 0 is the unique solution to where this equals 0. Or not equals 0, is as small as possible. It's the minimum. And then you can use that formula that you get for the derivative equals 0, and that will give you what the solution to this problem is. I'm not going to do that here because it's not very pretty, and it's hard to generalize. It's true, and it works, and you can generalize it if you really want to, but I don't want to. So, alright, so how are we going to do this? Well, AX, no matter what we pick for X, AX is in the column space of A. That's the definition of the column space, right? Is everything you can get out. So this is minimized when AX is the closest point in the column space to our vector B. Right? Because if it's the closest point, this is going to be the smallest possible vector, which will mean that this norm is as small as possible. So, so the solution to the least squares problem is when AX is the projection of B onto the column space of A. Right? So the least squares problem, this is an important term. It's just referring to trying to minimize this, make this as small as possible. This is a bunch of squares, things squared added together. So the least squares is trying to make this as small as possible. So yeah, this is the smallest when A of X is the projection onto the column space. Now, the reason why this is, remember, the projection is by definition the closest point on the column space to our vector. So if we find the closest point, by definition, we're done. We're good. We found it. So if the column space was one-dimensional, we'd be projecting onto a line, and this would be exactly the formula that we gave earlier in this lecture. But, of course, we're not. So we need to do something different. Or not different per se, just more complicated. We're actually going to use the same type of proof. So let's look at this in R3. The column space could be, say, a plane, just for sake of argument. Let's, I'm just drawing a picture. So our B is not going to be in the column space, because otherwise we'd just have an exact solution and all would be well. So what we want to do is we want to project it down onto the column space. We want to find this vector. And just a second. So yeah, we want to find this projection of B. Now, this projection, remember, is what we want A times X to be equal to, which is great. So, what we need, so this distance, or this vector here, is the error. Because the error is B minus AX, so, this vector minus this vector, exactly, great. We want to make this as small as possible. Remember, if we want E to be as small as possible, if we want to get the projection, that means that this line, that E in particular, which defines that line, has to be perpendicular, has to be orthogonal to the column space of A. So, we need that the error is orthogonal to the column space of A. But recall that the orthogonal complement of A, or of the column space of A, the orthogonal complement, is equal to the kernel of A transpose. We already proved that. So if we want E to be perpendicular, orthogonal to the column space, that means that really what we want is that we want E in the kernel of A transpose. These two statements are the same. So we want E to be in the kernel of A transpose. So the best solution is whenever A transpose times the error is 0, but A transpose E is just A transpose B minus AX, and we can reduce this to be A transpose AX equals A transpose B. This is a very important equation called the normal equation. So, to just explain why this is important, what we just showed, what we just talked about, is that if x hat solves A transpose A x hat equals A transpose B, then x hat solves the least squares problem. That's what we just showed. Now, a couple of things. One, this is not at all obvious. I mean, we just showed it, right? I mean, it works. It certainly works, but this is not obvious. It seems kind of weird that you just multiply by A transpose, and all of a sudden, you get a system that you can just solve and get the the least squares solution. It seems kind of magical, really, and it is kind of magical. I'll be honest. The other thing is, the proof of this is very interesting, and understanding it will help you understand all of these concepts that we've been talking about. I know I went through it kind of fast. Fortunately, this is recorded, so you can just listen to it 2 or 3 more times until you understand it, or you read it in the book. They have a little bit of a bigger explanation in the book, and let's see what else. And they also actually have another slightly different way of saying that they prove it. So again, this is these are the normal equations. We do that plural because this is a matrix equation, so in general there's going to be more than one equation. And so all we need to do is solve this, and we're done. All right, so let's write this again. If x hat solves A transpose A x hat equals A transpose B, x hat solves least squares problem. What we just said. So it turns out that A transpose A, of course, might not be invertible. Now, in general, in real applications of this, it almost always is. And the reason why is because, generally speaking, you have more data points than you have equations. Then you have like variables. Then you have variables. So if you do 100 experiments and you have 3 variables, the chances of them being linearly dependent are virtually nil. Of this not being invertible are virtually nil. So, but in particular, we do have to be careful because this is a math class. A transpose A is invertible exactly when the columns of A are linearly independent. So this is the columns of A we're talking about, not of A transpose A. I should mention, A transpose A, if you just look at the dimensions, is a square matrix, so that's not a problem if we want to find an inverse. But it's invertible exactly when the columns of A are linearly independent. Let's see. So, why is this? Well, remember, if the columns of A are linearly independent, that means that R, by definition, has to equal n. And so if we're thinking of this as a map from Rn to Rm, then what this represents is that if the columns are linearly independent, that means that there's no kernel. So, the row space, if you will, is everything. And so, when you map into Rm, you have the column space of A, which the dimension of this is n, right? That's R equals n. And then you do have some sort of co-kernel. And there's nothing you can do about that. But the point is, then we map from here to here is invertible, right? We just talked about the map from the row space to the column space is invertible. And we're not inverting it here, right? We're just multiplying by A transpose. But A transpose sends all of this back to 0. And so it's not going to mess with this, right? Here to here, it's going to be invertible. You're not going to get, when you go here to here via A and then go back to here with A transpose, you're not going to get the same vector in general. You might, if you get lucky. Essentially, if A is orthogonal. You might get the same thing, but generally speaking, you won't. But you'll still get all n dimensions, right? Because the rank of this map is R, the rank of this one is R, and it's going to work out. And so this is not a proof. You could make this rigorous if you wanted to. It's not too difficult. But yeah, this is the reason why. So, to erase this picture for a second, or forever, I guess. What this means is, so if that's true, then we can find x hat very easily, right? By just A transpose A inverse, A transpose B. That's just, by definition. So, this is the solution x hat, right? So the projection of B, remember AX was supposed to be the projection of B. And so the projection of B onto the column space, of A, is equal to A times x hat, or A transpose A inverse A transpose B. Now, you might think that this is funny, because why didn't I, from here, why didn't I just multiply both sides by A transpose inverse, and just get AX hat is equal to, well, A transpose inverse and A transpose cancel out, we just get B. So we get the projection as B. The reason why you can't is because A transpose is not going to be invertible, in general. I mean, it could be, of course, but in general it won't be invertible. And so because of that, you can't do the formula here. This is not equal to A inverse A transpose inverse, which is what the normal thing would be if A were invertible. If A were invertible, this would be true. And then these would all cancel out and be great and everyone would be happy, but it's not. So you can't. All right. So, yeah. So what this tells us is if we want to project a vector onto the column space of A, so the projection onto the column space of A is given by the matrix, well, we have it right here. A transpose A inverse A transpose. This is the general projection matrix. Now, you may not believe me, but it does in fact turn out that if A is, the column space of A is defined by a single vector, then we do get exactly what we had before, the A transpose A. These two are the same thing if the column space of A, or the column space of capital A is a single vector. All right. But I mean, obviously this has to be more complicated because we're dealing with multi-dimensional spaces, you know. We could be projecting onto a 7-dimensional subspace of R25, and of course it's going to be more complicated. So we have to deal with it. All right, so I just wanted to do a really silly, or not a silly example, but a really basic example. So let's say we have, mark this as an example, 2x equals 4 and 3x equals 5. So if we think about this, the answer should be somewhere between 2 and 3. Just because, you know, the answer to this one is 2, the answer to this one is, between 1 and 2. The answer to this one is 2, the answer to this one is a little less than 2, so it should be somewhere in between them, right? And in some way that's fair, it should be somewhere between them. So if we wanted to write this as a matrix, we would get 2, 3, x equals 4, 5. This is a perfectly great matrix A, so we need to multiply both sides by A transpose. So we get 2, 3, 2, 3, x equals 2, 3, 4, 5. We solve this, we get 13, x equals 23. These are 1-by-1 matrices, which are really easy to solve. So x equals 23 13ths, or x hat, if you will. And this is our solution. It checks our, gut check. It's between 1 and 2, so it's at least not obviously wrong. And so we're good, right? We're done. This is the least squares solution. This is the solution that makes the error here as small as possible. So what is our projection? So here's A and here's B, if you will. The column space of A is 2, 3, right? There's only one column, so that's the column space. It's defined by that. So if we project B, we should get something that's some multiple of this. And the projection of B is 2/3 times, which is A, times x hat, which is 20, 30 13ths, which equals 46 13ths and 69 13ths. That works great. And you can check, this is But 3.54 and 5.31. But the point is, this is, you can check, this is some multiple of this vector here. So we get that, well, obviously it is, right? It's 23/13 of it. And you can see that, this is close to here. It's similar, but we moved it. We got the closest point that's on the line defined by 2, 3. All right, so at this point we're mostly done. I just want to say one or two more things. Oops. Oh, actually 3 more things, but you know what. All right, so we're going to do some special cases. So if B happens to be in the column space, so if it happens to have a real solution already, then we can say that there is some AY, some Y, so it's AY equals B. That's the definition of B being in the column space of A. There's some linear combinations of columns of A that give you B. There we go. So PB is, remember, A transpose A inverse A transpose B. That's the definition that we just gave, or the formula we just got. But B is AY. We can just replace it here. Then we have an A transpose A and an A transpose A inverse, so they have to cancel out. And so the projection of B is itself, which makes sense, right? If it's already in the column space, the closest point in the column space is itself. So this is just a confirmation that our formula makes sense for it to be a projection. 2. If B is perpendicular to the column space of A, which could happen, then the projection of B is 0. So, why? Well, if this is true, remember the orthogonal complement to the column space is the kernel of A transpose. So PB is again A transpose A inverse A transpose B. That's the formula. But there's an A transpose B. So since it's in the kernel, it has to be 0. All right, last thing. Oh, I already said this, but if A has rank 1, so if it only has one linearly independent column, then A transpose A is equal to A transpose A, little a, and X hat equals A transpose B over A transpose A as before. So, it's pretty straightforward at that point. So anyway, that's the lesson for today. Next time on Monday, we'll talk a little bit more about least squares problem. I'm not sure exactly how much more I want to go into details and how to set things up. We may end up going on pretty quickly from least squares to the next section, but we'll see exactly when I plan for the lesson. All right, thank you. Have a good weekend.